Hello everyone and welcome back to the Ansys Fluent Academy Beginner CFD Series. This is lesson 5 and today we will be looking at the important classical problem in the fluid mechanics, Couette Flow. In this lesson, we will set up a simple 2D simulation in Ansys Fluent to understand Couette Flow, and we will also see why this case is such a useful benchmark for CFD beginners. So, what exactly is Couette Flow? Let's look at the schematic here. We have two parallel plates with fluid between here and here. The bottom plate is stationary while the top plate moves with a constant velocity. Because of viscosity, the moving plate drags a fluid along with it. The velocity of the fluid increases gradually from the bottom to the top, starting at the zero at the stationary plate and reaching the same velocity as the moving plate at the top here. So this creates a linear velocity profile shown here by this line. The arrows represent how the fluid speeds up as we move upward. That is the basic idea of Couette Flow, simple but very important. In this tutorial, we will go step by step through the process just like we did in our previous 2D tutorials. First, we will create the geometry in SpaceClaim. Then we will generate the mesh in Ansys Meshing. After that, we will move to setup, run, and post-processing in Ansys Fluent. And all of these steps will be done inside Ansys Workbench, keeping the same workflow as in the earlier lessons. So let's get started. Here, as you can see, this is our geometry. We have a stationary plate. We will call it as bottom wall with 50 intervals, and the moving upper wall, which is the top wall, as our boundary condition, has the velocity of 1 meter per second. We will use the water liquid for the liquid that in this problem. The length of this plate is 20 millimeter and the width is 1 millimeter. And we have two periodic boundary condition in the left and right side with 10 intervals for the mesh. The height is chosen small because the only variation happens in the vertical direction and we don't need a large gap to see that. In fact, Couette Flow is scale independent. The same physics apply whether the gap is 1 millimeter or 1 meter. So let me go to the workbench and start this project. So first of all, we can save the project. So I will save this one in this working folder. I will call this project as a Couette Flow and save the project here. Like other previous lessons, I will drag and drop one Fluent here. And then I will double click here to rename this one as a Couette Flow. Like the previous tutorial, we will use the SpaceClaim as the geometry. The default geometry here is the SpaceClaim, so I can double click to open the geometry. But before that, you will see I need to change the analyze type from 3D to 2D as for our 2D analysis. So I will double click here for opening the geometry and you will see the starting SpaceClaim in the status bar here. So let's wait a few seconds to open the SpaceClaim. Okay, now we are in the SpaceClaim. So we need to create a rectangular with this dimension 20 millimeter in X direction and 1 millimeter in the Y direction. So for this purpose, we need to be in the sketch mode as we are. And now I will select the rectangular here. Then I need to select a sketch plane. So I will click here and then I can select the XY plane here and then click on the plan view. So Now we are here. So I can select the origin point as the start point of this rectangular. The unit is millimeters, so I can directly type 20 millimeter for X and then use the tab key on the keyboard and then put 1 as the millimeter and press enter. So this is the rectangular with the specified dimension. So I can click on the end sketch editing. So as you can see, this sketch will be changed to the surface. And now for this left and right side boundary, I will call these two as periodic left and periodic right. So for this to do so, I will go to the groups here, group tab, and then if I just use a select tool and then select this left edge, I can use a create name selection or use Ctrl G as the short key. I will click on the name selection and then I will call it as periodic left. I will do the same for the right side edge. Select here, use Ctrl G and then write periodic right. Now I can select the bottom wall and call it, I will first use create name selection and call it as bottom wall here. And finally, I will select this wall and then use Ctrl G and write it as top wall, which is this edge here. So this geometry now is ready for go to the meshing process. So I can just simply close the SpaceClaim even without saving, and then finally I will just save this project in the workbench. And as you can see, the geometry task has been done. So now I can simply click on the mesh to open the meshing mode, and you can see meshing is starting to open. Okay, so the geometry, as you can see here, has been important to this meshing mode, and you have your name selection here, periodic left, periodic right, bottom wall, and top wall. So now we can go directly to the mesh. As you can see here, we need 15 intervals in the X direction and 10 in the Y direction. So we need to use some sizing. First of all, I will select the sizing here, and then I can select both bottom and wall together and click here, apply. Then change this element size to number of division, and then change this one to 50. Change the behavior to hard. So this part has been done, divided to 50 division. And then another sizing for the vertical edges. So I will go to the insert and sizing. I will select another sizing. Then we are in the geometry selection, and it is geometry selection mode. So you need to click here, select the left, and then hold the control key, and then select the second one, and then press and apply. Change the type from element size to number of division, and then use 10 divisions for these two, and change the behavior to hard. And finally, as we need a structured mesh, I will go to the mesh, insert, and use face meshing to give a order for the meshing to have a structured mesh. So for the geometry selection, I will select this face. As you can see, the icon changed to face as I'm here on the face. Press and apply, and you can see it is a mapped mesh and method is quadratic. So it is now ready to generate our mesh. I can click here on the mesh and then right click and then generate the mesh. Now, as you can see, we have 10 division intervals in the y direction in both, and 50 in the horizontal ones. You can go to the statistics here, and as you can see, we have 500 elements, so that is correct. So meshing mode is also done, and it is ready to send an update in the workbench. So I right click here and use just simply update the mesh, and you can see there's a message that this mesh successfully transferred to Fluent. So now I can close this meshing mode also here. And you can see this part has been checked also. So I can just press simply click on the save button and project is saved. So now it is time to start the ANSYS Fluent here. I will double click here. So before that, I will just reset this setup and then double click again to open the Fluent launcher. As you can see, it is automatically choose the 2D dimension as we choose geometry as 2D, and then use double precision and increase the number of processors to 4, and then press on a start button. As you can see, Fluent is starting to be opened. Uh, then we can start with this general setup. So we are working in the pressure base and STD, and we can keep all of this setting here. Then I will go to the outline view here and start our setup from top to bottom of this tree. We can start with the model. For now, I will keep this energy equation off, but I can activate it also later, so I will keep it off for now. Then I will go to the viscous model, and as this is a laminar model, not turbulent, so I can select laminar and press on OK. So in this case, we don't need to do anything in other model. And after that, I will go to material and fluid. As you can see, the aluminum is the default solid material and air is default material for fluid. So I need to add one new material as water liquid. So right click on the fluid, click on the new, and then go to the Fluent database here, click here. And then at the end of this list, you can find the water liquid here. So you can just click on the water liquid and then copy into your database. And as you can see, water liquid has been added under the fluid. So I can close this one and also this window. Now we have water liquid in our library under fluid. So now we need to go to the cell zone condition under the fluid and change the default material from air to water liquid. So I can double click on the fluid here. And then simply in this window, I can switch from air to water liquid and then press on apply button and finally close this window. Now it is time to define our actually boundary condition. For the internal, you don't need to do anything here in this part, but in the wall, as you can see, we have all of this boundary condition under the wall, bottom wall and top wall. The type of these two are wall, and so this is correct, so we don't need to change anything here. But as you know, we are going to use these two periodic left and right as a periodic boundary condition. But if you want to change this one and right click here on the periodic, if you see here, there is no periodic type of boundary condition here in this list. So you need to change actually the type of these two boundary condition from the console. So before changing this periodic left and right from wall to periodic, I will go to the bottom wall and top wall to check if we need to change anything here or not. The bottom wall is a stationary wall, so we can keep this one as a stationary and just close this window and then open the top wall. But as you can see here, it's a moving actually wall with the velocity of 1 meter per second. So we need to change this wall motion from stationary to moving wall. When you change it, so now you can specify the speed of this wall, which is 1 meter per second, and it's transitional in the X direction. So I keep this part as a default setting and only change this value from 0 to 1 meter per second. And then finally press on apply for the top wall and then close this window. Now it is time to change the periodic walls from wall to periodic. So for this case, this is a new thing that you are learning in this lesson 5. So you need to do some changes from console. So as you can see, if you click here and press simply enter, so you can see you have some options that you can access to these ones. To change the periodic the boundary condition and specify those ones, we need to use the mesh items and use some settings here. So you can just simply type mesh and press enter. So as you can see, we moved under the mesh now, and if I press enter one more time, I will go to the subcategory of the mesh. So I will click enter on the keyboard. So there are a lot of options that we need to use one of those for changing wall to periodic boundary condition. And this is actually modify zones. So you can simply type modify zone, or another way is to just select with the mouse this command or part of this one, and then press on the scroll of the mouse, the middle bottom of the mouse, and as you can see, it will copy here. So you will simply access to this one, and after that you can just simply press enter on the keyboard. So now you are under the modify zones. And here the place that actually you can change your wall boundary to periodic. So you can just press enter to go to the sub folders of this modify zone here. And then you need to select the make periodic here. So as I explained before, I can select this one, make periodic, and then press a scroll of the mouse. And now you have this order here, and then press enter. So now you need to specify actually the periodic zone that you are going to actually use here, and this is the zone ID here for your wall boundary condition. As you can see, for bottom wall it is 7, periodic left is 5, periodic right is 6, and the top wall is 8. So periodic zone, we will select the periodic left, so I will just simply press 5. And then for the shadow zone, you need to select the second periodic zone. So this is a periodic one that will be repeated in the X direction. So for the shadow zone, you will press 6, which is this one, zone ID of periodic right, and then press enter. And for this question, rotationally periodic? No, it is not periodic. So the default is yes, so you need to write no and press enter. And then it is asking to create periodic zone, and it is yes, so you can press enter or just type yes and then press enter. And auto detect transaction vector, press yes or press enter. So now, as you can see, we changed our periodic zone here. So now there is a new boundary condition here, periodic, this one. I will just close this too. So now we have our internal periodic and also the wall. Now we have two walls, this bottom and top. And now this is the periodic zone. Actually, I can, first of all, I can display again as we change some boundary. So I can go one by one. For the bottom wall, as you can see, this is our previous bottom wall, and now also. Then I will select top, and this time those two periodic left and right change to just periodic zone. So if I select this one and display, you can see these two are our periodic zone, and this is actually the domain of our problem. I will just keep this one, but if you want, you can simply click on the edit and change the name to another thing like periodic. Or maybe I can also change it. I will change to periodic, apply. After this rename, so you need to display again as we have a new name here. I will display this one and close here. Now everything in the boundary condition is done. I can go and to the method and check. So I will keep default in this problem here. Then after all, I will go to the control and check something. This solution control, I will keep these ones also as the default. And finally, I will go to the monitor and the residual. So double click to open this one. First of all, check that these two are checked. It means that if the residual will be print to the console here, and also we have a plot for the residual. As you can see, since there are three differential equations to be solved in a 2D incompressible problem, there are three residuals to be monitored for convergence, one each for the continuity, x velocity, x momentum, and y momentum equation. And Fluent lists this as continuity, x velocity, and also y velocity, as you can see here. The default convergence criteria are 0.001 for all three of these, but experience has shown that this value is generally not low enough for proper convergence. So I will change this one to E minus 6 and then press on the OK to exit from this window. And as you know, actually Fluent doesn't allow you to start iterating until you initialize. The solution scheme in the CFD codes start with some wrong solution of course, and iterates towards a more correct solution. It needs an initial guess to start with. So we need to go to initialization here, and I will select the standard initialize. And as you can see, all the initial values are set to 0. Which are fine for the problem at hand. This sets the velocity to actually 0 everywhere in the flow field except the upper wall, of course, here, since it is moving to the right. As the code iterates towards a solution, the effect of moving upper wall will be felt deeper and deeper into the fluid later. So I will just press on initialize. And now I can go to the run calculation here. For a start, I will just select 200 for the number of iteration and then press on the calculate here. As you can see, then div 200 number of iteration actually doesn't, I mean, with this number, we didn't reach to the convergence. Only the calculation, the number of calculation has been completed. And if you check, y velocity is under 1e minus 6. But we need more iteration for continuity and x velocity. So I will increase this one to 800, and then I can also change this reporting interval to from 1 to 10, since there is no need to display every iteration. And then I will again press on the calculate. So I will keep this setting for current and future calculations also and press on OK. And then we can wait for a few minutes. OK. And as you can see, we reached to our convergence here after 740 actually. The solution has been converged actually. And now we can start our post-processing and actually check our results here in the Fluent. First of all, I will display mesh again, but without the interior actually display, only the boundary condition here. So actually Fluent enables a user to define a surface or line at any desirable location. In this example, a vertical line parallel to y-axis in this direction will be defined at the center of this channel. This line will be useful for creating a velocity profile, which can be plotted here. And as you know from previous lessons, the profile data can also be saved along this line for comparison and post-processing later. So to do so, we need to go to the surface and create a line. So now I can go to the results, and under the surface and create, I will select lane or rake and then press on line and rake, and then just actually open this window here. For the name, I will name it as vertical in the center, something like this. And then we need to define 2 points, one the starting point and one ending point. So we need x0 and y0. So in this case, as you know, the dimension is 20. So the center is 10. So I will, and the dimension is in the millimeters, so I just simply write 10, and the y is 0, so we are here. And then for the top point, it is 10, and y is 1. And if I go here under the surface, you can check we will create one line here. So I press on the create, and now I have this vertical center. I can display in the mesh display here or here, and now you can see we have this line under these surfaces. So I will play and display, and you can see we have a new line called vertical at the center. So I can close this two window for now. We worked a lot in the previous lessons with the XY plot. In this section, a velocity profile at this newly formed line will be generated, and this data will be plotted and will also be saved on a text file for post-processing later. So I can just go under the results XY plot and select a new XY plot. I will call it, for example, as vertical. And then as it is in the y direction, I will just change this position on x to position on y. So it means that we will use the, this vertical line as our position, and then change x1 to 0 and y to from 0 to 1. This is the plot direction. So Now we need to select x-axis function. Here I will select the velocity here, and then under the velocity magnitude, and under the surfaces I will select this vertical center in this one, and then just check that this node value has been selected, so I can just simply click on the save, and now I have this plot here, and this is the velocity magnitude on the that vertical line, and this is our y position from 0 actually to 1. Here this is the 1, so I can just go for the x-axis auto range. I will change 0 to 1, and then change this format from exponential to float, and then press apply, save and plot again. And also I can select the major rules for y direction, apply, and also this one x, I will select the major rule also here, and then apply and save and plot. Also I can change this color to the dark red, for example, and then save and plot. We can change everything here. And this is the setting for the axis. So I can close this one, and then this time I will go to the curves. So for the curves, I can also select the color, for example, dark red for this case, apply, and then save. You can see here, I can increase the size also from 0.3 to 0.6, apply and save and plot. Now I can just close this one. And finally, I will write the data to a text file. I will select the write file and then press on the write here. And I will call it as vertical dot xy, and then you are under this dp0 under your working directory, ff and Fluent, and then press on OK, so the file will be saved. And now I can close this window. And as you can see under the plot, XY plot, you have this vertical, and you can edit it later. And this is the working directory that I'm working on, Couette Flow. I have Couette Flow files here. If I go to dp0 and under this triple F, I have the Fluent folder, and this is a vertical text file. I can open it with the notepad, for example, and you have access to this data on a text file. So now I can close this one, and maybe generate some streamlines and save a streamline profile value for post-processing. And now to generate the streamlines, we can use the contours. So I will go to contours and select one new contour here. And to see the range of values of stream function and its unit, actually first I will here go to the velocity, select the velocity, and then I will select the stream functions. And you can see this minimum and maximum are set to 0 as a default. So to see the range of these values of stream functions and its units, I need to press on compute. So this is the minimum and maximum of the stream functions. The unit is kilogram per second here for these two, the Couette Flow. And now to see the stream functions contour, I will just simply click on the save and display. And this is the stream function of this Couette Flow, as you can see here. And under the graphic, I have this contour. I can call it as the stream. Save it again to save with this name here. So in this contour, as you can see, these streamlines actually are lines that are tangent to the local velocity vector everywhere in the flow field. They show the path a fluid particle would follow at an instant in time. So for steady flows, they are identical to path line. And as you can see here in the Fluent, they are generated from the velocity field you solved for. For our Couette Flow tutorial, you will see straight parallel lines between the two plates because the velocity direction is uniform and there is no curvature or recirculation. So as you can see, there are some parallel lines like this one. You can also plot with the banded type. Now I can close this one and again create a new XY plot for this stream function. So again, I will change this X position to Y and then change X to 0, Y to 1. And this time I will select velocity, and this time instead of velocity magnitude, I can select the stream function and then select this vertical center line. I can also call this one as a stream function and then save and plot here. As you can see, this is our stream functions in the y direction. I will go to the axis and change the y from auto range 0 to 1 millimeter. Apply, close, save and plot. And also I'm going to change this to float, close this one, and then save it again. Okay, perfect. And now we can calculate forces on the lower and upper walls. Actually, Fluent has an option for calculating the force on any wall. In this example, the forces on the bottom and top walls of the channel will be calculated and compare. But before that one, please let me go to the XY plot stream function and save this stream function, write to file, then stream function and XY, press OK, and then close it again. And now we can go for calculation of forces on the walls. So for the force, you can go under the report and select the forces. So there is this option to calculate the force. And first, I will select the bottom wall. Since we are interested only in the component of the force in the x direction, the default force vector of 1, 0, 0 is appropriate. So to calculate and view, I can press the print, and under this console, you can see the data of the force for this bottom wall. So as you can see, the data are available here. The forces, both pressure and viscous component, are displayed on this main Fluent window in the console. I can record this one and write as a force on bottom. So I can just write as force bottom. I can extend this window a little bit more to see all the data actually here, and this is the net value. Now I can do the same for the top wall, so I just change the bottom to top and then again print to the console. I can also write it as force top. So if I extend this window a little bit more, just let me keep it first here, and I can close this one, increase the size to check and compare both forces on bottom and top wall. In our result, we can see the shear forces reported on top and bottom walls. Here and also here. This is for bottom wall and this is for top wall. We can also check the total here. On bottom wall, the viscous force is positive, while on the top wall here it is negative, but nearly the same in magnitude. This makes sense. In Couette Flow, the shear stress is constant across the fluid, so the moving top wall drags the fluid forward, and by Newton's third law, the fluid pushes back on the wall with an equal and opposite force. So the same shear force is then transmitted to the stationary bottom wall at the bottom. And that is why the forces are equal in magnitude, but opposite in direction, which also confirms our simulation is behaving as expected. So that is a good sign to check our results. Okay, now I can decrease the size of this console, go to Workbench and save the project here and waiting for this status bar. So again, back to Fluent. And so from this part, I'm just adding the energy equation to this 2D Couette Flow. So this procedure enables you to add and solve the energy equation in this simple Couette Flow problem with the Fluent. So now I'm going to create a new plot here. Click this time a new XY plot. This time I'm going to plot X velocity. I will change this one to Y and then 0 to 1 velocity, and here you can select the X velocity and again select the vertical center, the line in the center of our geometry, and then again save and plot. So I will not go to change this axis. I'm just write the data as the x velocity dot xy, then press on OK, save it again. So with this plot we checked actually the velocity in the vertical line at the center of our domain. So now I can close this one, and to actually activate the energy equation, I can go to the physics here, or just simply go to the models and open the energy equation and then tick this energy equation and press on OK. So this will turn on the energy equation. So when we activate this one, we can go to the viscous laminar. So this option will be activated after activating this energy. So if I disable this one, it will disappear. And when I activate this energy equation, so viscous heating will be an option. So I can tick this viscous heating and then press on OK and activate this viscous heating. Now the thermal boundary condition need to be specified in the actually boundary condition. I will close this one, and in the boundary condition for both walls I will open boundary condition. So go to the thermal tab, so it is activated. I will change the thermal conditions to temperature. and keep this default temperature 300 Kelvin and press on apply. Close this window and this time open the top wall, which has the 1 meter per second velocity. It's a moving wall, and then again go to the thermal tab and change this heat flux to temperature. Keep the default value. So it means that the bottom then I will apply and close this one. It means that both bottom and top walls has the same thermal condition, temperature 300 Kelvin. So as we activate the energy equation, if I go to the residual, you will see the energy also has been activated here. This time I will deselect this check convergence for all these 4 equation, and then I can press on OK. So this will enable you to iterate to matching accuracy and go run to run calculation. This time change this number to 200 and keep this reporting interval to 10. So I will select the calculate, use this setting and press OK. So just go to this residual, press an OK, as you can see here. So just keep iterating, monitoring these results. So as you can see, after a while, the residual should all level off at a very low values here. You can also check here. They are very low values. You may have to for more than 1,000 iteration, but it shouldn't take a very long time. And as we uncheck the check convergence in the residual plot, so it will continue. So I will just put 1,000 and calculate. Use this setting again. Just wait for a few seconds to reach the end of iteration of this. As you can see, 80, 10, and it's done. Calculation completed. And if I go to the scaled residual, you can see the residual plot here. Now I'm going to generate a plot of temperature profile. So I will go to the result XY plot, a new XY plot, and I call it as a temperature vertical. Change this one to y-axis again. This time temperature and static temperature, vertical center. And as you can see, I can close this one. Go to the temperature vertical. Unfortunately, since the temperature differences are only a fraction of a degree, the resolution of temperature axis is not very good, especially there may not be enough variation in temperature for the x-axis to be labeled properly. Unfortunately, since the temperature differences are only a fraction of a degree, the resolution of the temperature axis is not very good. Especially there may not be enough variation in temperature for the x-axis to be labeled properly. So I can go to the axis here for the x-axis. I can just change this general to float and change this precision to 6 and then apply and save. I also can disable this auto range and use something like this, 300 0 0 0, this one, this value, apply, save. So as you can see, this variation is a little bit more visible. You can change this value, and then so you can have a better resolution of this plot. So actually it makes more sense to plot temperature difference than the magnitude of temperature itself here. So I will show you how we can use some customized function for the temperature difference. I mean temperature minus 300, for example, in this case. So for now, I will just close this one and this window. So to do so, we can go to the user define and use this field function, and then I will click here on this customize field function calculator. To define a temperature difference, I will click here and then select temperature, a static temperature. Press on the select, so you have the temperature here. You will use this sign here and then type 300 as 300 Kelvin. So this is the definition, and I can change this name, temperature difference, and now I can press on define to define this function. Now I can close this one. Again, this time I will go to the temperature vertical to this plot that we have here. So in this case, instead of temperature, I can go at top of this list, use the custom field function, and here we have this newly created function. I will select this one, and this time I can plot, but I will reset this one to auto range for this one and save the plot. So as you can see here, this is the temperature difference on this vertical line. So as you can see here, temperature differences is 0 because at the bottom wall here and this top wall, the temperature is 300 Kelvin and the temperature difference 300 Kelvin minus 300 Kelvin will be 0. So the temperature difference here is 0. And when you go to the middle of the your domain in the center point, so the temperature difference is a little bit more, and this is this value actually. I will also write this one to a file, temperature difference .x y, and then I will press on OK, and then I can close these two together, both of this window actually. Now I'm going to do some changes in our bottom wall. I can open it and change the thermal condition. Change this one to the heat flux. So as you can see, the heat flux default value is 0 watt per square meter. So it means that this bottom wall is a perfectly insulated wall. So I can keep this one, press apply, and then close this window. Then I can go again to the run calculation, keep this value, and I will iterate until the temperature profile converts to a nice smooth profile for this case. So I will press on calculate and OK. I can go to the scaled residual. I can close this one. OK. And now I can go again here in the temperature vertical, these temperature differences actually, and then I can save and plot this time. So you can see that this temperature difference is totally different with the previous one. We still have the temperature difference at the top wall at 0, but for the isolated valve, which is a bottom valve, we have the maximum temperature difference. We can also load the previous file to compare. So if you use the load file here and use this actually temperature difference here, press on OK. So you have this file here, and when I select this one, you can compare these two cases. The first one is actually for the problem with two valves with the same temperature, 300 Kelvin, and this white one is for the second case, which we use the heat flux 0 for the bottom valve. So with this tool, XY plot, and load the previous file, you can simply compare two plots together like this, two different cases actually. So now this is our post-processing in these two simple Couette Flow. I can close this one also here. So that brings us to the end of our 2D Couette Flow tutorial. I can first close this Ansys Fluent here, and then save our project. Actually, in this lesson, we saw how to build the geometry in SpaceClaim, generate the mesh in Ansys Meshing, and then set up, run, and post-processing the case in Ansys Fluent, all inside Ansys Workbench, just like in our previous tutorials. We also reviewed the results. The velocity profile was perfectly linear, and the shear forces on the top and bottom walls were equal and opposite, matching the analytical solution for Couette Flow. This makes Couette Flow a great validation case for CFD and an excellent way to understand the effect of viscosity and shear stress in a very simple setup. In the next lesson, we will move on to another classic CFD problem. Thanks for watching, and see you in the next tutorial.